So calculate the integral of f of x, y, z is equal to this beast, square root of x squared plus y squared plus z squared, e to the x squared plus y squared plus z squared, over the solid that is in between the spheres. Okay, x squared plus y squared plus z squared is equal to 4, and x squared plus y squared is equal to 9. So again, like we did last time, let's go ahead and parameterize our surface. Okay. And actually what we're going to do, since we are dealing with spherical coordinates, we're just going to go ahead and take these spheres and we're going to put them in the spherical coordinates right away. Okay, so first let's go ahead and draw our solid. Okay, so let's say that this is a sphere of radius 9. Okay, and then we have a smaller sphere inside of radius 4. Okay. I don't know why the Pokemon just jumped into my head, but this is, maybe it's a Pokeball? I don't know. Maybe it's like Voltorb inside a Pokeball. Alright, I'm under it. Anyway, so the solid that we're integrating over is everything in between here. Actually, this is more kind of like an egg, but not egg-shaped. Anyway. Okay, so just envision that for a second. Okay, so let's go ahead and convert this straight into spherical. So what would rho be going from? So rho, okay, remember rho is the radius of the sphere, right? So rho would be going from, if we take a slice, okay, this way. Rho is going from the outer sphere, which is radius 3, okay, and the inner sphere, which is radius 2. Okay, so rho would be going from 2 to 3 in this case. Okay. Now, what would theta be going from? So notice we're trying to get the whole entire sphere, right? So that means we want an entire rotation. Okay, so theta really needs to go between 0 and 2 pi so that we get our whole rotation this way. Okay, around sort of like the equator. Think about that of our crazy solid here. Now, what does phi go from? Okay, so we want the entire sphere along the, what is it called? Longitude? Yeah, there we go. I always have to remember latitude or longitude. Latitude is flat, right? So that would be like your equator. So yeah, around the longitude, so this direction. Now, notice that theta is going from 0 to 2 pi, which is giving us our entire rotation around the equator, right? So we only actually need phi to go from 0 to pi, so that we just get the top point all the way down to this point, and then theta is taking care of the rotation there. Okay, so this would be the spherical coordinates of this solid here. Okay, so when we go to integrate, we're actually in pretty good shape, and notice that all these are constants here, so our lives are a little bit easier. Although again, since this is a triple integral, it's going to be a little bit more complicated. All right, so our triple integral over this solid of, I believe it's square root of x squared plus y squared plus z squared, e to the x squared plus y squared plus z squared, dv is going to be equal to, and again, since they were all constants, it doesn't really matter what order we do this in, but I'll try to go in the order of your book, which I believe was d rho, d theta, d phi. So remember, rho is going from 2 to 3. Okay, it was bouncing between the sphere of radius 9 and 4. Okay, to get the entire spherical region, we needed theta to go between 0 and 2 pi. And then to get the whole sphere again, we needed phi to go into, or go from, I should say, 0 to pi. Okay. Now, one thing I want to point out too, if you went from 0 to 2 pi, let's say for phi, because you're like, wait, you need to get all the way around, you would actually be double counting, because let's say we have a sphere, and I take this point, okay? Actually, let's take a point on the other side of the sphere. So let's pretend like this point is on the back side of the sphere. To get to that point, all you have to do is rotate this far down, okay, from the z-axis, and then spin all the way around to get that point. So you don't actually need to go all the way around the Earth or the globe or whatever your sphere is to get to that point. All right, so that's a tangent, but in any case, keep that in mind. All right, now what about our function? What's our function going to look like? So let's go back to our conversions, and I want you guys to look. Okay, where do you see x squared plus y squared plus z squared? Notice we have that right here. Okay. And notice also this equation tells us that rho squared is equal to flat out x squared plus y squared plus z squared. Okay, so this actually turns our equation or our function into something pretty nice. We'll just have rho e to the rho squared d rho d theta. Whoops, and notice that I already forgot something. Remember that we have to multiply by phi squared, rho squared sine of phi. Rho squared sine of phi. Oops, I almost drew theta there. Okay, d rho, d theta, d phi. All right. To make our lives easier, again, what we're going to do is we're going to be a little bit tricky. First, let's go ahead and simplify this. It looks like PEP almost. This is going to be triple integral, and I'll forget about the bounds just to save a little bit of time. Rho cubed e to the rho squared sine of phi. But let's go ahead and change. Let's integrate with respect to theta first, just so we get that integral out of the way. Then let's integrate with respect to phi, and then let's do rho. Okay, and again, because all of our bounds are constants, we can just flip away like Fubini's theorem tells us. So let's see, what am I doing? I'm doing d theta, so that's 0 to 2 pi. Then I'm doing d phi, that's 0 to pi. And then, whoops, rho is going from 2 to 3. Work smart, people. Work smart. All right. So if we integrate with respect to theta, notice theta is nowhere here. Okay, so the integral of this would just be this whole thing times theta. So we'll get the integral of 2, 3, integral from 0 to pi of rho cubed e to the rho squared sine of phi. Oops, and I'm actually going to use soft brackets there. Okay, times theta, evaluated at 2 pi and 0, d phi, d rho. Okay, if you plug in 2 pi, notice that you're just going to get 2 pi. If you plug in 0, you get 0, so this ends up just being a 2 pi, and we'll go ahead and pull that constant all the way on the outside. Okay, so that 2 pi is taking care of this bit. Not beta cubed, rho cubed. Yeah. All right. D, C, D, rho. Now let's go ahead and integrate with respect to rho. So the integral of sine of rho, that's going to be minus cosine of rho. So let's pull out the minus sign out here to the front. 2 pi, integral from 2 to 3. Rho, I don't know why I want to keep writing beta. Rho cubed e to the rho squared. There we go. Okay, it'll be cosine of phi. Again, I move the minus sign on the outside. Evaluated at pi and 0. Okay, d rho. Okay, and notice if we plug pi and 0 into this, what we're going to get is minus 1 minus 1. Okay. And here, let me put parentheses around what we're actually getting there. Okay, which is going to give us a minus 2. And I'll go ahead and pull that out on the outside. So this will become minus 2, which means we'll have a 4 pi now out front. Rho cubed e to the rho squared d rho. All right, so then our integral, we just have to solve this now. Go in. Okay, so we had integral from, and I already forgot, from 2 to 3, and we also have a 4 pi. 4 pi integral from 2 to 3, rho cubed e to the rho squared d rho. Okay, so what we're going to do first, let's go ahead and do a u substitution. Let's let u be, actually, no. Because I know where this is going, I'm going to actually call instead of u, let's call it w. Let's let w equal rho squared. Okay. Then dw equals 2 rho d rho. Divide both sides by 2. So we get dw over 2 is equal to rho d rho. Okay, so that'll turn our integral into 4 pi over 2, and over 2 is because of our differential here. Integral, let's see, if rho is 2, w is 4, if rho is 3, w is 9. Okay, now what happens here, we're going to get, so remember rho cubed is rho squared times rho. So we're going to get a w, e to the w, dw. Okay. I'll let you take a second just to check that, or convince yourself that that's what we're going to get. So notice, and I'll just give you a little bit of guidance there. The rho squared is going to become the w, which is what we got here, and the extra rho becomes that differential there. Well, in addition to the d rho here, but okay. Now, how do we integrate something like this? Remember, we have integration by parts, and this is why I didn't want to use u earlier. So we're going to integrate by parts, so we're going to let u be w. dv is going to be e to the w dw. Okay, v. No, continue recording. Go back. There we go. V is going to be equal to integral of e to the w is just e to the w, du, dw. So this will become 4, actually let's go ahead and simplify that. 4 pi over 2 is just 2 pi times, okay, so u v, so w e to the w, evaluated at 9 and 4, minus, go back. Let's see, the integral of, so uv minus the integral of v du, so e to the w dw. So this is going to give us, and notice the integral of e to the w is just e to the w there, so I'm just going to evaluate straight up. We're going to get 2 pi times 9 e to the 9th minus 4 e to the 4th minus, okay, antiderivative of e to the w again is e to the w, so all we're going to get from this is e to the 9th minus e to the 4th. Okay, so simplifying this a little bit, we're going to get 2 pi. So we can combine these. We're going to get a 8 e to the 9th, and then minus 4 e to the 4th plus an e to the 4th is going to give us minus 3 e to the 4th. Okay. So again, just like we had in cylindrical coordinates, integrating in spherical coordinates is a long process. So take your time and think about it. Okay, change order when you need to, and work smart.